Hello everyone. In this video, we are going to talk about transistors. So a transistor is one of the, or I can say the most probably important semiconductor out there, which basically is the foundation for most of today's electronics. Okay, from simple ones to very advanced ones, almost they are in everything, every chip. Most of the stuff are made with transistors, because they can do lots of different functions, but their main functions are amplifying signals and switching purposes. If you watch one of my previous videos, I showed you an RC circuit with a transistor switch. So we can use them to basically do very fast switching of electric circuits, but we can also use them in amplifications. And when we make operational amplifiers, op amps, we can do lots of things with op amps. We use them in all sorts of different circuits. So then they come in lots of different shapes, right? There are BJTs, FETs, MOSFETs, all sorts of things. So we're going to see lots of different shapes of transistors, but most of you probably have seen this shape or this one most of the times. So what is a transistor? We're going to see. But first, know that there are two major categories of transistors. One group called bipolar junction transistor, or BJT, and the next group called field effect transistors, or FET. So BJT and FET are the two major transistors. So first, let's look at BJTs, the class that is very common, this group, and use them a lot. So they are a three-layer semiconductor. So you can hear they say NPN or PNP transistor. What is that? Let's take a look. So it's basically like you bring two diodes. Remember, diodes have a P region and an N region, or positive and negative, and a depletion region in between. So now if you bring two diodes and put them head to head, you can have a PNP or NPN, right? So here you brought an NP and a PN and put them head to head, or here you brought a PN and an NP and put them from the N side together, right? So you get NPN and PNP transistors. And so you can merge these two regions together and get three regions, one N, one P, one N, or the other way. And we give them different names. So the three major entries, or the three major connections that these transistors have, are called collector, C, B is base, and E is emitter. Okay? So what are these? So let's look at, for instance, an NPN transistor. So this is the P region of the two diodes that we kind of merged together. Of course, not by a wire, but you made it like this since beginning, right? So you kind of join them together, but again, not with a wire. And so this is like one of the diodes on this side, one of them on the other side, and the depletion regions in between. So this is an NPN. Now, the side that you call emitter, here it is shown on the left side of this. Here it is shown on the right. So these two are kind of flipped version of each other. But emitter is the region that is highly doped, and it can basically send out a big charge and inject charges. So if you look at it like a basically valve, a controlled valve or switch, emitter is the part that sends you the electric current, a big current, okay? And collector, the other side here, or as I said in this case, this side is the side that collects the charge from the base, and base is the middle terminal that basically acts as the major switch. So depending on how much current you send it in BJT, you can turn that switch on or off, okay? So this is a lightly doped layer that controls the flow of the current, okay? So if we want to learn about that, we can look at this analogy here with a mechanical system, a fluid system. So here you can see these pipes, and there is this valve here, this kind of L-shaped valve. And the position of this L-shaped valve is controlled by the push from this base. So if you push this base forward, it is going to create a moment about this pin, and it is going to make this guy rotate. When it rotates, then the current is going to come from collector and goes to emitter. We say the transistor is on. If you don't push too much on it, and you cannot make this member rotate, it is going to block the current from collector to emitter. We say it's off. Now, this is a mechanical analogy, but in a transistor, what you do is a current that you send through the base. And depending on the value of that current, if it's high enough, then the current will come through collector and goes to transistor. That switch is on. If that I is not, this I of base is not large enough, then this is gonna stop working, and basically the switch is gonna be off, or the circuit is gonna be open. Okay, so first of all, they are what we call current-based valves or switches, because everything is controlled through the current, the small current that is sent through the base. And then I of the base and I of this collector come together, and they are added together and becomes I of the emitter. So I of the emitter is going to be I of the base plus I of the collector, because that acts like a junction. But again, whether this opens or closes, that depends on the value of the base here. Okay, so this is an NPN transistor that the current flows from collector to emitter, and then we'll see the PNP is kind of the opposite of that. So let's talk about it right now, since I mentioned it. So these BJTs, there are two major types, NPN and PNP. In NPN, you see there are three legs: collector, base, emitter. The current, as you can see, is going from collector to the emitter, right? As you can see here. So the positive side is collector, the negative side is the emitter. And in order for it to run, you have to have some current in the base. And also the voltage between the base side and the emitter side should be at least something like 0.6 volts or something like that. So base voltage has to be bigger than emitter voltage. When base voltage is bigger than emitter voltage by at least 0.6 volts, then the switch is going to be on. If V of base is less than emitter or the same, then there will be no current going through the base, and the circuit is going to be what? Open, and the switch is going to be off. Now, PNP is the exact opposite, as I said. If you look, the current is coming through emitter and goes to collector. So emitter is the positive side, collector is the negative side. And for this circuit to work, the current that you send to the base should be negative. How can it be negative? It becomes negative when the voltage of emitter is bigger than base. So this side has more voltage than this side, so the current is going to go this way. And this difference, again, should be at least like something like 0.6. So the current can go through the base. Okay? So in this case, I of the emitter that comes in minus I of the base that goes out is going to be I of the collector. And again, if you take this negative to the other side, you get the same equation. Okay? So this is the difference between PNP and NPN. Now, to clarify a little bit more about the difference between NPN and PNP, other than in one of them, current goes from collector to emitter, in the other one from emitter to collector, I just want to a little bit explain the difference between them. So if you just saw, other than this first difference that I mentioned, the base activation in NPN was positive voltage, right? You see that base has to be bigger than the emitter, positive voltage. So your switch mid-wire should be bigger than where you're sending the current to. In here, it's negative. E is bigger than B. Another thing that they say NPN is used for low side switching or low side drive. This PNP is used for high side switching or high side drive. What is that? So let me show you that one here. So in here, you can see that I have my base of the transistor is attaching to my input voltage, and there is this resistor in between to limit the I of base. The emitter is attached to the ground, and the collector is attached to the LED that I want to turn on. My load, the place that I have the load or drive, is on what side? We say it's on low side. Why do we say this is on low side? Because in here, the switch is between what and what? It is between your basically low side, which is the ground, and your load. So the switch is between your load and your low side, which is the ground, so we call it low side switching. So the connection between the light and the ground is going to be disconnected if I turn the switch on and off. On the other hand, in high side switching, you see that the switch is between what and what? It's between your power supply Vn and the load. There is no switch between the load and the ground. Load is already grounded on one end. The other end of it can be connected or not connected to the power supply. So you see here, the power supply is not directly connected to the load. It goes like this. This current never goes to the load. So it's never connected to the high voltage, high side Vin. But in here it is. So this is a high side switching because your load directly get it from the high voltage Vin. In this case, it is directly connected or not connected to the ground. So we call it low switch, low side drive, or a low voltage switching or low side switching. So if we want to directly connect our load to the power supply, we use a PNP. But if we want our load to be connected to the ground, then we use NPN. And then here, clearly the majority of the load are electrons. Here, it's the lack of electrons or holes. So it makes basically NPNs a little bit faster than PNPs. And that's why you see most of the time NPNs are used a lot more than PNPs do. Because in electric circuits, you care about the stuff being done fast. So in digital and logic circuits, you mostly use NPNs. PNPs are used in systems that are running based on battery and the power circuits. So if you want to know where and when to use PNP or NPN, hopefully this table can give you a little bit insight about when to use NPN versus PNP. And these are the two major types of what we call bipolar junction transistor or BJT. Okay, now let's look at the governing equations a little bit and operation modes and some of these graphs and some example, right? So first we want to look into those and phototransistor, and then we're going to go to field effect transistors or FETs. So first thing, let's look at the governing equations. So here you can see an NPN BJT, and you have a resistor on the collector side, you have a resistor on the base side, you have I of base, you have I of collector, you have I of emitter, and there are power supplies VB and VCC, which we'll get to them. But a simple equation here is, as I showed you, I emitter is I of base plus the collector. That's your current through the nodes, right? C and B are coming to the switch and E is going out. So that is Kirchhoff's current law or node law. The other thing you have here is VCE, the voltage that exists between C and E, between collector and emitter, is equal to VCC, the voltage that you have on the collector side, minus RCIC. And this is basically writing a loop, the voltage across this loop for the collector emitter side. Okay? Now, the most important formula in a transistor is what we call a current gain, beta. Beta is the ratio between the collector current and the base current. This ratio beta, which we call it the current gain or DC current gain, that is an important factor in a transistor. In data sheets, instead of calling it beta, you're going to see HFE, okay? So if you see HFE in data sheet, don't be surprised. HFE is the same as beta, the current. And if you search for what's the meaning of each one of them, this H here means a hybrid parameter. Here I just typed them for you. This F is for forward current transfer, and that E is for emitter, common emitter configuration. Okay, so beta or HFE is the most important parameter. We call it the gain or DC current gain, which is I collector over I base. And from here, from these two, you can see that I of the emitter is going to be, this is beta times IB. And this is IB, so it is going to be 1 plus beta times IB. Now, of course, this gain is not a constant thing. It depends on some parameters, and we are going to talk about it. So basically, this gain, as we'll see later, that depends on the VCE voltage, the voltage that is between collector and emitter. Okay, you can see that is your beta, and it also depends on the collector current. Okay, so you see that here, basically for a specific current in collector or emitter, one or base, one of them, this is how this beta changes versus V of CE. It's really a function of VCE, okay? And this is that VCE we just talked about. So I'm going to show you more equations and example here in a second. So this is an example, and I'm going to go through equations and show you one example to use these. But before that, we need to know a few more things, and those are the operation modes of the BJT. So there are 3 modes of BJT. First one is cutoff mode. That is where the switch is off, okay, and no current flows. The other one is called the active or linear mode, okay, this area here, which in this mode you use a transistor for amplification to bump up the current. And there is a saturation mode, which is this area here, and that is where you use it for switching, basically. So there is linear mode for amplification, saturation for switching, and cutoff where actually it is basically off, okay? It's not doing anything. So what is the linear region? In the linear region, as you can see, the slope is very mild. In other words, you can say that although in this linear region, the voltage across collector to emitter, VCE, is changing significantly, but the current in the collector, IC, does not go too much up and down because the slope is very, very minimal, okay? Let me bring this down so you can see better. So as I go in this linear region from right to left, as I move in this direction, what's going to happen? Go from this point to this point. You see that my voltage collector emitter has a huge drop, okay? And also you see that the current in my collector is highly correlated with the current in my base. So you see that between these different curves, which are plotted for different base currents, I get different ICs. So if this is IB1 and this is IB2, which is bigger than IB1, clearly you see that for the same voltage, IC2 is also what? bigger than IC1, and the difference between these two IC1 and 2 is very similar to the difference between IB1 and 2. So the IC and IB are highly what? Highly correlated. What does that mean physically? Means if I keep this VCE constant at some number, let's say at 8 volts, I keep that voltage between collector and emitter at fixed 8 volts, then if the current that I send to the base to turn the transistor on, off, or move it into one of the linear or saturation regions, if I make this current a little bit bigger, like for instance 2 times bigger, probably the current that I get from the collector is also going to be about 2 times bigger. Okay, so they are highly correlated. On the other hand, we have this other region on the left side of this dashed line, which we call it the saturation region. In the saturation region, if you look on the left, what would you have on the left side? So here, as I mentioned, you can see that the basically change in VCE is not too much. As I go from this point to this point, you see that all VCE is changing is only this much, as opposed to in the linear region is with this much. So here, clearly, the change in the voltage across the collector emitter is not big. It's very small drops. And also, the relation between IC and IB is not that clear. You see here again, bigger IB means bigger IC, right? But here, that's not the case. You can see that although when not deep into the saturation region, bigger IB means bigger IC, but at some point, all of these curves will merge into a single line, which is this line. Now, along this line, it's not clear that which IB you're belonging to. So when you are at one specific IC level, you don't know which one of these IBs, this top one or this bottom, the second one, are basically showing IB. So IB and IC are not showing clear correlation or relation between themselves. Okay? Another way to say it is the transistor VC voltage is not affected by the base current in this region. So if I go from this curve to this curve to this one, you see that the difference in VCE is bare minimum, okay? Because the width of this region, as I said, is bare minimum. Now, what about the beta, that gain, IC over IB? What gain do you get in the linear region? What gain, current gain, do you get in the saturation region? For that, we can look at this other graph. These graphs are available in data sheets of transistors. If you look at this graph, which is beta versus voltage, this is an interesting one. So look here. This is the graph done for a fixed collector current 200, and there are different kind of betas versus different VCs. Look here that in this region, the change in VC is very minimal, very small. That corresponds to the saturation region. In the saturation region, the change in VC was very small. That's the same thing here in this region. And how much is beta in this region? How much is your gain? Well, that is 10, that is 100. This number is 20. You see that in this region, on this side, on this green side, your beta is 20 or below, okay? So below 20, below beta of 20, you can say that this side is kind of the saturation side. This is the side that the voltage CE is not really showing much of effect. On the other hand, this other region, this side, where your gain can go up to 100 and above, this side, you see that your VCE is changing significantly. So this side here is basically similar to your linear region. Okay, and your beta gain is typically bigger than 20 all the way to 100 and more. Beta can go way more than 100. So typically smaller beta values, smaller gain values are corresponding to saturation, and bigger gain values corresponding to amplification. And that is exactly what we want. We want in the linear region where beta is big, we want to use amplification because IC is beta times IB. And IE is beta plus 1 times IB. So for a fixed IB, if beta is bigger, these currents are going to be bigger, and I'm amplifying, let's say, by 100, 101. But in the switching state, which we use in saturation, my goal is not to make the current so big. Here, beta is less than 20. My goal is not mainly increasing the current. My goal is to turning it on and off. Okay, so these are the regions that you have in a typical transistor. Now, another way to explain this and talk about it is, as you can see here, in the switching state, in the saturation state, in the switching operation, we want VCE to be as small as possible. Why? Here you can see a diagram, and I'm using this transistor to switch basically your voltage here, make it on and off. This is V plus, this is your load, right? You see that you're doing a low side switching with an NPN transistor. And if you look at this path here from V positive to 0, look at this path. If you look at this path, you can see that V plus minus VCE, correct, is basically going to go to the minus V of load, of course, is equal to 0. Or if you want, you can switch those. So let's say V load minus VCE. Okay, so that's the, and why 0? Because the end of it is ground. So this is what you have. And clearly you see that if you solve for V load is what? V load is going to be the V plus minus VCE. So if I want most of that voltage to go to the load, I have to minimize the amount of VCE. Okay? And under what condition your VCE is the minimum that is out there? If you look at any of these two graphs, the top one or the bottom one, you clearly can see that the minimum of the VCE, the leftmost region, is the saturation region, right? The minimum VCE that you have is the saturation region. The minimum VCE that you see here you have is in the saturation region. So you want to operate in the saturation region, okay? So that is very important. And the reason also is that if you minimize VCE, then VCE times I that goes through the collector, you know, V times I is the power that is being dissipated. Then VCE IC, when you minimize VCE, then the power that is dissipated in transistor in terms of heat will also be minimized, right? Because you're bringing down the voltage across it. So the heat that is wasted in transistor is minimized, and most of that power and voltage is sent to your load. Okay, so to minimize the loss, you want minimum VCE. To get minimum VCE, you have to operate in saturation mode. That's why in switching, we operate in saturation mode. But in amplification, we go in linear mode. That's where we can apply bigger IBs, we get bigger ICs, and we got large betas, more than 20, typically all the way to 100. Okay, now here, this other graph, before we solve the example, this is another graph that is interesting. It shows the voltage versus IC for a specific, basically, gain, right? And V, when we say voltage, we mean voltage CE. So if you look here, for operating in the saturation region, which is beta less than 20, let's say for beta of 10, so here beta is 10, we are working in the saturation region, you see that your voltage CE is, first of all, minimum. Okay, it's very minimum. If you plot this for other ranges of IC, clearly in the saturation range it's minimum, and it depends on the IC itself. But you see, it's mostly, if you look at this range, it's mostly somewhere around 0.2. Okay, so if you work with the gain of 10 or something, mostly the voltage that is also very minimal, the voltage CE is going to be what? About 0.2. We're going to use that in this next example to solve the problem. So a rule of thumb, a 0.2 volt for VCE in the saturation region is something that we can work with. Now let me demonstrate all of these things that I said in this example. So here we have NPN transistor, we have a low side drive or low side load, and Vin that we have is 5 volts. This V plus is 10 volts. We have a light that has 100 ohm resistance. We have a 2.2 K ohm resistor in the base path. The emitter is connected to the ground. We want to know, under this case, this transistor Q1, first of all, is that on or off? Second of all, does it work in the linear region for amplification, or does it work in the saturation region for what? For switching. Okay? And if it is in the linear region, how would you change this circuit so it works in the saturation mode for switching? Okay, so here we have to figure out beta, and based on beta, we can judge, based on the range of beta, whether it's working in the linear region or the saturation region. But first of all, is this on or off? So the first thing we can calculate is I that goes through the base, this I here. Well, I of base is equal to what? Is equal to this V of N, which is on its left side, minus the voltage that you need here between base and the emitter, so V of base emitter, which is the same as V of base, right? Because your emitter is 0. So V of base emitter, this is the same as V of base, divided by that 2.2 kilo ohm. Now, as I said, most of the time, if you look, the voltage that you need for these transistors to turn on is about 0.6 volts for base to emitter. Well, VBE is 0.6. So if I use a 0.6 here and I use a 5 here and calculate this current, your current is going to be about 2 milliamps. And this is bigger than 0, of course. And we remember that if under this voltage the current is positive, then your switch is in the on mode. Okay, so I'm sure that clearly my Q1 transistor is on. But does it operate in the saturation region or does it operate in the linear region? That's the next thing we need to find out. For that, we need to find beta. Beta is IC over IB. IB I already found, 2 milliamps. So if I can find IC, I can find beta and then make a judgment. But how do I find IC? Well, IC is this current here. In order to find it, we have to go through this path. So in that path, we have 10 volts minus V of CE, which is the same as V of C, because again, E is 0. If I divide that by this resistance of 100 ohms, that is equal to IC. Now here, as I said, VCE is the same as VC because V of E is 0. So how much is VCE? As I said here, you can see that if you assume that you are in the saturation region, so for a moment, because here you have two unknowns, IC and VCE, and you don't have both of them. But if you go and look at this graph, as I said, in the saturation region, you can see that your V of CE is somewhere around 0.2. So if I replace that with the 0.2 in this case, and calculate IC, you can see that your IC is going to be about 98 milliamps. And if I plug a 98 milliamp here and a 2 milliamp for B, the ratio for beta that I get is 49, which is quite a bit bigger than 20. And you see that although I assumed you are in saturation mode and your beta is like 10, 20 or smaller, but your actual beta that you calculated is way bigger than that. That means that you are not working in saturation region, and right now you're operating in the linear region with the way that it is set. If you want to work in the saturation region, this beta has to be quite a bit smaller. And in order for this beta to go down, you either need to make the collector current go down or make the base current to go up. Otherwise, you cannot operate in the saturation region, okay? Now, of course, in this case, you cannot change the value of the light or the lamp resistance. That's your load. You cannot change your load. The only thing you can do is to change R2. So if I make R2 a little bit smaller, then IB is going to go bigger, and bigger IB means a smaller beta. How much? So here, let's say the ratio that you want is, for instance, something like 10 or something, right? So let's say that the beta that I need to have is about 10. So if I go back here, let's say the beta that I need is about 10, because I want that assumption of 0.2 that I used to be valid. So I am going to use this ratio of 10 here. Now, if that's 10 and that 0.2 is good and everything, and this 98 is good, your IB should be about 9.8. And if this is about 9.8 and you plug in 9.8 here, you see that this 2200 should be should be quite a bit smaller. Now, if you look at the book that I'm using, my reference, which is the reference I'm using all the time, this mechatronics book, you see that the number is a little bit different. So they used 9.4 here, and the ratio they use is 10.5. And for that, you need to change this 2200 to 470 ohms. So if you change this to 470 ohms, your IB current instead of 2 is going to be 9.4 mil. It brings your data to about 10, for which this VCE of 2.2 is correct. Now, since your beta is 10.5, quite a bit less than 20, you can say that now you are working in the saturation region. So you see, all I need to do to operate this transistor for switching and in the saturation region is to use a smaller base resistance. If I make this resistance very large, then I bring down the current. Bringing down the current of base means bigger beta. Bigger beta means it goes to the amplification and linear region. And in the linear region, you're going to get lots of heat generated around the transistor, okay, and from the transistor. So in order to make this just do the switching job without too much heat is to reduce to reduce the resistance R2. So hopefully now those governing equations and those graphs make a little bit more sense to you and in which mode we are operating the transistor. Okay, so before I move on to the FET transistors, there is one category of transistors that I need to talk about, a category of BJT, which you probably have heard is called the phototransistor. And they might be transparent like this or not transparent. This is where the base terminal, the basically switching terminal of it, is so large that in order to make the switch on and off, you don't need to send it current. Instead of sending current through this, you just shine light at it, expose it to light. And the energy of the photon that it receives is enough to create a small current in it and switch it on and off. Okay? So these phototransistors are used in lots of different devices, including optocouplers and optical encoders, where on one side you have these LEDs that are turning light, correct? So these LEDs are shining light, and then you have this wheel here with these holes in it. So every time the hole comes between the phototransistor and the LED, it allows this light to go and get to the phototransistor. So the phototransistor turns on the switch, so it will record a pulse in the circuit, whatever circuit it is, correct? And then when the next hole comes in, again, it does another pulse. So you are going to get a train of pulses, each pulse per one of these holes. So if you count how many of these pulses you have, you can count how many of these holes have passed between the transistor and the diode. And let's say if you have, for instance, 30 of them every 12 degrees or so, then every 30 pulses means one full rotation, correct? So it tells you exactly the angle that your system has rotated. So you can use an optical encoder, okay? And these phototransistors are used in that. So you clearly see that's the symbol of it. And you see that the P part of it, which the base goes to, it is basically controlled by light. And the IC versus VC graph for it is basically like this. Okay, so you see that this is the collector current, this is the collector emitter voltage, and this is drawn per several H values. And what is H here? As you can see, it is in watts per centimeter squared. So it is basically power divided by surface area, right? So this is the light power over what? Over surface. So if you know the term irradiance, that is the amount of irradiance, or the surface, basically the energy per time per surface, which is received by the base. Okay, so you see, depending on how much energy it is receiving, the amount of current that is created in collector at a fixed voltage is going to go up, of course. Okay, so here you don't have I of base. Remember, in this graph, you had I of base to be the controlling factor of IC versus VC, because that's how you control the switching. This time your switching is controlled by irradiance instead. And these are different things. And again, you can see there is a saturation region and there is a linear region here. Okay, so the behavior is very similar. Now, the next group, the second group of transistors, are what we call field effect transistors, or FETs. Okay, and they are mostly voltage control transistors as opposed to current control. Okay, so you apply some voltage to this pin that is called gate, and that is how you control to make this switch on and off. So it has 3 pins. These pins, instead of collector, emitter, and base, are called source, drain and gate. Gate is the one that controls the flow. Drain is where the current exits. Source is where the current enters. So for NPN, you can say that this is similar to collector. For NPN, this is similar to emitter, and this is similar to base for NPN. For PNP, then the place of collector and emitter is reversed. Okay, so first thing is they are voltage driven. The switching is decided based on voltage to the gate, not current. And there are two types of them, similar to NPN and PNP BJTs. For FETs, there is N channel and there is P channel FETs, okay? And here I mentioned in this table their differences, and I can go over that, but let me show you here the logic. So here you have the gate, you have the drain, and you have the source, and this is for N channel, which is similar to NPN. So in the case of this N channel, how would you make the current to go from the drain to the source? Okay, or not go. This is the off state, so there is no current going. This is the on state, that the current is going from drain to source. Okay, and you see for the current to go from drain to source, you need the gate voltage to be bigger than the source voltage here by something like 4.5 volts. And if it's less than that, then you can see that the switch is off. So clearly here the current is going from drain to source, and the voltage of the gate should be bigger than the source for N channel. For P channel, the current is going from source to drain. And for that, V of source should be bigger than V of the gate by, again, more than 4.5 volts. If it's less than that, again, no current, okay? So this is the difference, but you see very, very similar things to BJT. So if I want to summarize the difference between N channel and P channel, you can see that in the N channel, current went from drain to source, right? That's exactly what happened here. Look, it went from drain to source. But in P channel, it went from source to drain, okay? The N channel, the carriers of electricity are electrons. That's why they go fast. In P channel, they are the lack of electrons or holes. They are slower. The turn-on condition here, gate should have bigger than the voltage. Here, gate should have less than voltage than the source. The N channels, like NPNs, they are more common because of their speed and efficiency. The P channels, they are mostly needed when you are switching on the high side. The resistance of the N channels are lower. The ones for P channel are higher, and the N channels are typically faster than the P channels, okay? So these are two different types of FETs. Now, the FETs in general are in two subcategories. One group, we call them junction filled effective transistor, or JFET. This is where you have the two subgroups of N channel and P channel, just what I discussed. There is another group of them which are also very famous, called MOSFETs, and they are called metal oxide semiconductor filled effect transistors. These MOSFETs, they have insulated gates, which makes them to be very fast in terms of switching and very efficient. So they are more expensive than the JFET transistors because of the metal oxide that is inside them, makes them faster, makes them more efficient, and they are a little bit more expensive, but they have some important properties like faster switching and higher efficiency. And similar to the JFT N channel and P channel, they have two categories, also two subcategories. One group called enhancement, types called enhancement mode, that they need a positive voltage to turn on, and then there is depletion mode that needs a negative voltage to turn on. So if we want to look at these transistors that we have seen so far, there is the category of BJT and there is the category of FET. And these BJTs are NPN and PNP. And these FETs are JFET and MOSFET. JFETs are N channel and P channel. And MOSFETs, as you can see, basically you have these two types, enhancement mode and depletion mode. So this is like the overall taxonomy or categorization of transistors, okay? Now, here, these MOSFETs also, they have a logic level MOSFET and a non-logic level MOSFET. In logic level MOSFETs, the voltage that you need is 4.5, but in non-logic MOSFETs, the voltage that you need should be 10 or more. Another difference that these FETs or MOSFETs they have with respect to the BJTs is their current voltage diagrams. If you look at here, this is voltage of drain to source and this is the current through it, okay, which is basically this guy here going through. If you look here, the linear region and saturation region are swapped. If you remember the BJTs, the saturation was on the left and the linear was on the right, but here that is the opposite. The saturation is on the right and the linear is on the left, okay? And the reason for that is if I paste this picture that I got from the book, if I show you here in this picture, it kind of explains what is happening. It says if you look at this region near origin, you see that different gate source voltages, right? If you look at them for different gate source voltages, you see the behavior of current through the transistor and the voltage of the transistor, the behavior is perfectly linear, right? So that's why we call this region of I versus V, we call it the linear region, because unlike the BJTs where all of these lines will converge, all of these curves will converge into a single line, in here they are not converging to a single line. If you go back and look at the graph for BJT, you see that here, look, this curve, this curve, this curve, they're all converging to one single line. But not for MOSFETs. They are not converging to things. So this region, we call it linear. Now, why do we call this region saturation? The reason is, you see that here, regardless of how much I change this drain to source voltage, your I is going to reach a constant level and will never increase. So basically, regardless of my control voltage, how much I am applying, the current does not change. And in the book, there is this interesting term. It says the transistor is on in this point, and it's as on as it can be. That's very interesting. So you cannot make it more on or off. Your current is staying at a fixed number, not changing, and we can call it saturation. Now, if you look at the BJTs, that was not the case. Here, you see that your current is changing. Although the slope is very mild, but it is still increasing along these lines. You see it's still going up. but for MOSFET, it just goes pure flat. Okay, so the linear region and the saturation region for these MOSFETs and BJTs are different. Now, now that we learn about these different types of transistors and subcategories of them, let's go back and look at, we said the two major categories are BJTs and FETs, or maybe MOSFETs mostly. So when would you use any of them? When would you use this, right? When would you use them? PNP, NPN? How would you decide whether you should go with a BJT or FET in general, right? So here is the part that we need to discuss when to use either one, okay? And then I want to show you a little bit about reading transistor data sheets and a few of their applications. So please bear up with me. This lecture is very long because there is too much to say about transistors. So in this table, there is a comparison between the BJTs and the JFETs and MOSFETs. You can see that the BJTs, the initial ones that we studied, we call them bipolar. I'll tell you why. The way you control them is by the control current that passes through the base terminal or base pin. So they are current-driven transistors and it's gone through the base. The flow of the current for them is collector to emitter or emitter to collector. Their impedance for input is low. Their noise level is high in exposure to temperature or thermal stability. They are less stable compared to other types. Okay. The gain for them, we call it beta or voltage gain. Actually, it's current gain, not really voltage gain. And their applications are mostly in amplifiers and digital switches. Okay, so actually this one is current gain, DC current gain. Then the JFETs and the MOSFETs, they are all what we call unipolar. Again, what is that? I'll tell you. The way you control these FETs all is through the voltage that goes to the gate. So by applying voltage to the gate, you can turn them on and off. And the current for them goes from drain to source or source to drain. Their impedance are high or very high. For MOSFETs, you see it's very high. For JFETs is high. And all of them have low noise level. Thermal stability of JFETs are better than BJTs. And for MOSFET, it's a lot better. Okay? Their gain characteristics is called transconductance. I can talk about that. And then their applications, as you can see, in low noise amplifiers and RF radio frequency circuits, in microprocessors, in power electronics, special switching applications. Now remember, I said MOSFET, there are two groups, enhancement mode and depletion mode. Okay? So clearly you see the difference. If you want to create an amplifier with minimal noise, you have to use FETs and preferably MOSFETs, but definitely JFETs because the BJTs create noise. If you want it to withstand temperature, because many of them are used in amplifiers and lots of heat is generated and you want them to work very well against heat, you want to go with MOSFETs. That's why in microprocessors that a lot of heat is generated, you want to use MOSFETs transistors, not BJTs. Okay? But if it's a simple amplifier, you don't care too much about noise, and it's a simple digital switch, you might get away with cheaper BJT. In general, as you go down this list, the price is going to go up, okay? Because you are getting more and more advanced transistors, more stable ones, less noise and so on, high impedance. So you're going to get more and more expensive ones. And there is one category that you might call it hybrid, which is a MOSFET and a BJT together. So they are called insulated gate bipolar transistor or IGBT. where again, through gate voltage, they are controlled, but their current instead of drain source is collector emitter. So you see there is a mixture in them. Their impedance is moderate, their noise level moderate, the stability for temperature is very good, and they have high power gains. So if you want to use them, you use them in motor drivers and power inverters. So in drivers of motor drives, you can use this mixed type or hybrid type, which is called IGBT. So as I said, I'm going to mention transconductance. Let me talk about it. So this current gain here, remember that beta was IC over IB, and some data sheets show HFE instead of that. There is transconductance, which typically shown by GM, and that is the delta in the drain current divided by the delta of the voltage between, basically, that's exactly what you have. These are these axes, right? This is your current, and the voltage is what? The drain to source. Basically, it's the slope over there, right? So that's the slope over there. And of course, this has to be calculated at a fixed VDS, at a specific VDS. That's the slope of that. And that is what we call transconductance. Okay. So for how much voltage you apply, how much change in current you are going to get. Again, that is the slope in this curve here. The slope of this line is, this slope is your GM, or we call it transconductance. Okay, so that is one thing I wanted to mention. The second thing I want to mention before we say when to use a BJT or MOSFET, of course, we have seen to a good extent when, and I'm going to mention a few extra things. One thing I want to clarify is bipolar versus unipolar. Okay, what is that one? So let me explain that. The BJTs, we call them bipolar. Why? Because they use both type of charge carriers. They use electrons and they use holes for conduction. Okay. In NPNs, as we learned, the electrons move from emitter to collector, but the holes move in the opposite direction. And in PNP, it's of course the other way around. Now, in FETs, which we call them unipolar, they are only using one type of charge carrier. For instance, in N-channel FETs, only the electrons are responsible for current flow. In P, only the holes. So bipolar or unipolar basically describes how many types of charge carriers are doing the work in the transistor. If both electrons and holes are there and moving, then we call it bipolar. If only one of them does, we call it unipolar. Okay. Now, going back to when you pick a BJT or a MOSFET, because MOSFETs are mostly more expensive. So we use BJTs when we only have a small control voltage. Okay. We might have enough current, but the voltage that we have is not a lot. On the other hand, we use MOSFETs when there is a lot of voltage, sufficient voltage, but not sufficient current. So, right? Because these guys are current driven, MOSFETs are voltage driven. So voltage is not the problem with MOSFETs, it's the current. And so when there is a small current, we can use MOSFETs, and when there is a small voltage available, we use BJTs. Now you might say, what if both sufficient voltage and current are available? Then which one you would choose? Well, it depends. Both of them can do the job in this case because you have both voltage and current to control them, but it depends. If the goal is to go with, as I said, smaller noise and better thermal stability, then probably you have to use a MOSFET or JFET instead of a BJT. Okay? Right? But if you don't care about that and you care about the price, then of course you want to go with BJT because BJTs are cheaper, okay? So, and MOSFETs are more expensive. Now remember, MOSFETs mostly do not need a base resistor, but still they are more expensive. And so this is all about now, what is it that you want to do? Okay, do you care about the price? Do you care about the thermal stability? Do you care about the noise? Another thing is, since in BJTs you use a base resistor, basically that resistor is gonna dissipate some energy into heat, so you're gonna get greater losses in switching, and so you're gonna be less efficient and greater heat dissipation in BJT. So MOSFETs are really much better. They are easier to work with and everything, but you have to pay the price. And here I made this simple table for you. And you can see that, for instance, if you look at the lower power category, a BJT can go from 10 to 50 cents. A JFT goes from JFET goes from 50 cents to $3. A MOSFET goes from 30 cents to 1.5. So you see these two are more expensive. Now you go medium power again, right? You see that still JFT is good. The thing is, when you want to go high power, you don't use a ton of JFTs, and you can use MOSFETs that can go up to $50. So in general, this category is a lot more expensive, the FETs compared to BJTs. And it depends on how much power you want to get and how much money you have. So now that we have seen those, let's go and look at the data sheet for a transistor and look at a few applications. And this example here, this amplifier example, by the way, has again some equations that could be useful. So how do you look at the data sheet of a transistor? Well, transistors have several pages typically of data sheet. And here we want to look at a BJT transistor, and here the goal is to use it as a switch. So if you want to use a BJT and use it as a switch, you have to answer a few questions in order to know whether you pick the right transistor or not. The first question is, how much voltage can your transistor switch? In the data sheets, that is shown by this parameter VCO-sus. What is that? CEO is basically collector to emitter, okay? That O is for off state, and sus means sustain. So what does that mean? Means the voltage from collector to emitter that your transistor can keep off, can cut, and can sustain, okay? If you look here, this is one of the transistors, okay? These are the category of transistors, TIP31. If you look at them, you see that depending on what category you're looking at, the voltage they can withstand and turn on and off is here 60 volts, 80 volts, and 100 volts. So if you want to basically cut a voltage in a circuit that is more than 100 volts, maybe you should not use any of these transistors. You should look into another transistor with a bigger VCO sustain. Okay, so that is one of the important parameters, is when the circuit is off, how much voltage it can sustain and keep off. That's the first thing that you need to look when you're looking at a BJT switch. The next question you should answer is, how much current can the device switch? Okay. Now remember, as we discussed, in BJTs there is high power dissipation, too much heat that is generated. So really, how good you can use a BJT is limited by the power dissipation specifications, right? So basically, are you using a heat sink with the transistor or not? How well you can get rid of this heat generated in the transistor. Because if you can't, you might not be able to use all of the powers of the transistor. So many transistors comes with heatsink. You have to pay attention to that. And this heat, this power dissipation comes from two sources. Last time we talked about the IC times VCE, the collector times voltage collector emitter. That was one of them. The other one happens in the base pin and the base path. I of base times V base emitter. Okay. Now, of course, this one is the bigger one because I of the C is much bigger than I of the B. Okay. So that is the bigger source, but this other one is also another term that you can add. Okay. So you need to make sure that your transistor, as I said, is not overheated. So what specs do you have for that? Well, here, if you go and look at the rest of the off characteristics, one was the voltage that we talked about. Now you have currents. So there are two currents that you can see. One of them is called ICO. The other one is called ICES. What is the difference here? So these are the currents that you can basically keep off. And if you look at their description, they are both collector cutoff current. Okay, so they are both ICs, right? The current that in the collector path, it can basically turn off. But what's the difference? EO and ES. So it's a current from collector to emitter. One of them is O, which is for open circuit. The other one is S, that is for short circuit. Okay, so if the circuit is open, how much current can it hold back? You can see that depending on the category of the transistor, it is 3.3 what? Milliamp DC. But if the base is shorted to the emitter, now they can only hold 200 microamp DC. Okay? So at most, the current they can hold and keep the circuit open is about 0.3 milliamp. And the voltage they can hold back is 60 to 100 volt DC in this case. Okay, for this specific category of transistors. Good. Now, the third question that you have to answer is, how much effort does it take to switch the device? Or in other words, we call it base drive requirements. So far we talked about making the switch off, holding the voltage or the current back and turning the switch off. So we looked at the voltages and the currents that it can hold off. Now, when you want to turn it on, you have to look at the uncharacteristic part of your transistor. And if you look here, there are some parameters that can help you. One of them is HFE. Remember, that's the same as beta. So you have some beta here, and you can see that beta, the DC current gain, is what? So there is, if you look in these columns, there is a min and there is a max. So your limits are between 10 to 50 for the scenario that the voltage that you're holding back is 4 volts and the current that you have in the collector is 3. So your gain is anywhere from 10 to 50. Okay. And now if, for instance, I of C is 3 amps and the gain is 50, how much is IB in this case? Well, IB is clearly IC divided by beta or HFE. So that is 3 amps and the gain is 50. If we go with the max of it, you can see that 3 over what? 50, which is basically 0.06, right? Amps. Or you can say 60 milliamps. If you want, you can say what? 60 milliamps is the current in the base frame, and with that now you can determine what resistor you need in the base path, right, and so on and so forth. And now since you have the voltage CE in this case, and you have IC, you can also determine the resistor that you need in the collector path. Okay, so if you want to determine these, you should be able to do that if you know V or CC, if you know V of B. So now you have the voltage from here to here, you have the current through here, and you have the current through here. So you should be able to determine both of those resistances if you know VCC and VB. Okay, so it tells you the type of currents that you need to send to base to turn it on for different gains. You can calculate those, and there are other things that you have. So what is the voltage CE and BE for saturation and for being on? So you see saturation, collector emitter saturation voltage for I of C of 3 and IB of 3.75, which is about a gain of less than 10. The voltage that you need for this transistor is 1.2. Remember, in one of our previous examples, the voltage that we used, voltage CE, was 0.2. Remember here? We use 0.2, about 0.2. In this case, is a lot more. It's about 1.2 for a beta of about 10 or a little bit less than 10. So this curve for this transistor is passing something like that. Okay? So you can see all of the on characteristics and the saturation characteristics here. Now, we want to look at the applications of transistors and to practice using these formulas again. The first application we want to see is amplification, because the switches, we have talked about them. I showed you if you want to switch in this example here, what is it that we need to do, correct? Remember this example that we solved? I showed you that if you want to stay in the saturation region, what kind of resistor do you need for RB and whether it is in saturation or linear region. Okay, now let's look at the applications of the transistors as the last part of this lecture. So we have seen switching in transistors. Now let's look at the linear operation in the linear region and amplification. So here is something that you use in audio and radio frequency circuit. So this is your NPN transistor. There is some voltage B that you put in behind the base pin and connect it to the base with a resistance RB. Then you have the voltage behind the load. There is some resistance for the load, and you have I through the collector, I through the emitter, and I through the base. So why does the circuit act as an amplifier? Let's take a look. So I through the base is equal to the voltage on this side, which is VB, minus the voltage on this side. Now voltage of that point is V of B with respect to E, because remember this point is grounded. So the voltage of that point is considered 0.7 in this case. Remember in the past we said that's about 0.6, so 0.6 or 0.7 doesn't make much of a difference. So here is 0.7 used, but we can say 0.6. So VB minus 0.7 divided by RB, that's the Ohm's law, this is equal to IB, the current for the base. Now the current for collector, IC, remember IC is beta times IB, this is IB, and beta here we also call it HFE. So that is beta times IB, that's the I of the collector. And this I of the collector passes through the load, so the voltage across this load, if we call it VRL, that is equal to RL times IC. Now if I look at this loop here, you see that VCC minus RL times IC is equal to VC or VCE basically, because the voltage of this point minus E, because E is 0, that's VC or VCE. That is the same as saying VCE. So VCE is, which is the same as VFC, is VCC, the voltage that you put behind this system, behind the load, minus RL times IC. And what is IC? IC is this guy. So I'm going to plug it right here, and then that whole term is going to go there. That is your IC. So you're going to get VCC minus RL times all of that. Now, if you rearrange it, the collector emitter voltage is going to be what? It is going to be this coefficient times VB plus this term here. Now, let's take a look here. If you look at this guy in parentheses, you know that's a constant value. Why? Because RL is fixed, RB is fixed, 0.7 is fixed, the gain is fixed for this specific operation condition, and VCC fixed. So this whole thing, you can call it constant C. V of B is the voltage that you have behind the base, and this guy here, that is a gain. So you can call it whatever you want, call it gain G. So you see that voltage of point C with respect to the ground, or E in this case, is equal negative G voltage of B with respect to the ground plus some constant. And this is, if you neglect this constant for a moment, you clearly see that you have an amplification of G. So clearly you are increasing the voltage that you apply to the base. You applied it to by G times and put it basically on the two sides of the transistor. And this G, if you look at it, is this G big or small? Well, if you look at the three parameters of it, one of them is the beta or HFE, and that is very large if you are working in the linear region. Remember, this HFE can be like 100 or bigger. And the rest of it is RL over RB. So if you make your RB smaller than the load resistance, quite a bit smaller, right? Because the load is not under your hand, but the base resistance is under your hand. So if you make that even smaller too, you see you can get a huge magnification, a huge gain. Okay, so you see that easily this NPN is used to magnify your voltage. And so it is used as an amplifier. The three other applications that I want to briefly mention, and I don't want to get into depth of them because each one needs its own basically lecture or video. One is power regulations in places that you need voltage regulators like motor drivers, consumer electronics, charging stations, stuff like that. You can use transistors just like what we did with a basic regulator with a Zener diode and a resistor if you watch my diode lecture. So here we can use a diode and a transistor and a resistor, and we can convert this voltage that is not necessarily always fixed and unregulated to a voltage that is reliable and regulated, okay? And that's where you see this kind of transistor. So this kind of circuits that have mostly transistor in them, these are basically some common things for voltage regulations. So when you see in this beginning of the video, you see this kind of basically transistor. They are typically like a voltage regulator. Although some voltage regulators, if you look at their shapes, they are like the MOSFET ones too. Then we have oscillators. That is where you want to convert kind of a DC voltage to some variable or AC voltage, like in clock generations or radio frequency transmissions. So here you can convert this DC voltage into some variable voltage by a combination of capacitor, transistors, and basically resistors. If you connect it to LED, you can see that the voltage through LED does change. And again, it needs analysis of its own if you want to do that. This is a simple oscillator. There are lots of other types of oscillators. And then, of course, signal modulation. So basically, you have a pulse and you have the modulating signal, which is kind of like a sine wave or something. And you want to basically convert these pulses into the form of this modulating signal. In other words, you want to get pulses for which the height of the pulse basically comes from the shape of the modulating signal. So if you connect these peaks together, the shape that it generates is this modulator signal. Okay, so you want to modulate this pulse and get this modulated signals, which is used a lot in communication systems. And again, my goal is not to go over that, but these are some common applications. But the major ones, as I said, are of course switching and amplification. And I know this lecture went very long, but hopefully I could teach you some basics about transistors, because transistors are very common. They are used a lot in electric circuits, and there are lots of things to learn about them. So all I did was try to give you like an intensive or a long, basically, introduction. Thank you so much for your attention. I'll see you in the next video.